Full screen. One problem that we had not discussed in our horizontal circles analysis was the rotor ride. In our horizontal circles discussions, we talked about the conical pendulum, something that swings a ball around in a horizontal circle. We talked about banked turns, where a car drives along a banked surface and maintains contact with the roadway. We talked about flat circles or flat surfaces where a vehicle relies on friction to maintain its curving path. So in these cases, we've got tension as providing some of that centripetal force. We've got a normal force, or at least the x component of the normal force and the x component of the tension, providing the centripetal force. A car driving on a flat surface, friction alone provides that centripetal force. And there's this other thing called the rotor ride, which is one of my favorite rides at the carnival, where you stand inside a vertically oriented cylinder. You stand against the wall with your feet on the floor, and as the ride spins around, you then feel pressed up against the outside wall. And once you're going fast enough, the floor drops out from below you, and you are now relying only on friction to stop you from sliding down the wall. Now imagine if that ride were at rest and the floor dropped out. Of course, when you're at rest and you're standing next to a wall, there is no force between you and the wall. There's no friction between you and the wall. And if the floor dropped out, well, so do you. And so as the ride spins, it causes you to be pressed against the wall to the outside. And this is where centrifugal force sometimes enters the conversation, where if you look from above, here's you pressed up against the wall. And so you feel as though you're being thrown outward to the wall. But in fact, that's not actually true. What's actually happening is your body would like to keep going in a straight line, but as you are trapped inside this cylinder, the wall of the cylinder gets in your way. And so it's not that you're being thrown outward from the cylinder. It's actually the fact that the cylinder wall is pressing inward against you exclusively with a normal force. And that normal force is what keeps you in this circular path. So we're going to look at this situation from the side view, sort of a cutaway view, where not from the top, but rather more back to that diagram, which I just erased a moment ago, where here's you along the side of the wall of the ride. The floor is not underneath your feet. And so we got to decide what forces are acting on you to keep you there. Well, of course, as always, we got your weight downward. Because you're being pressed against the wall because of that contact and the fact that you're trying to slide down the wall, that means that there's friction preventing you from sliding down the wall. So that's it. There's no wall. There's no floor underneath your feet. It's only friction between you and the wall that prevents you from sliding down. And as we just mentioned, the normal force is providing the centripetal force. So there's our free body diagram. Clean up our situation a little bit and then redraw that diagram. So here's our diagram. We've got friction upward, mg down, and a normal force providing centripetal force. So in the y direction, we've got friction up, mg down. Together, those are balanced because you're not accelerating up or down. But in the x direction, you are always accelerating towards the center. So the normal force itself is providing the centripetal force, mv squared over r. This is where we start. Well, this is where our forces, Newton's second law statements start. But I guess in terms of the given information, we're told that this rotor ride has a radius of 2 meters. Ooh, here's a tricky approach. The rotation frequency is 0.5 revolutions per second. So that tells us something about how quickly we're getting around the circle. We have to turn that into information we can actually use. 0.5 revolutions per second. So radius is 2 meters, 0.5 revolutions per second. Let's call that the frequency. Well, 1 revolution is all the way around the circle. 1 revolution is 2 pi r. It's all the way around. So I'm going to substitute that. So we got 0.5, half of a revolution, half of a circumference, half of 2 pi r per second in 1 second. So very quickly, this actually suddenly turns into a velocity because this 2 pi r is a distance. So we've got distance over time. So we've got half of 2, all right, so we've got pi times r, well, r is 2, so r times 2 in 1 second. Pi 2 times meters per second equals, that's a 3.14 times 2 is 6.28. So 6.28 meters per second is how fast we're actually going. So we've got a velocity we can work with, we've got a radius we can work with, and now we just gotta figure out our forces stuff. So friction, we always know what friction is. Friction is mu times normal. So mu times normal equals mg, and the normal itself, the normal force is that. All right, so let's sub that in. Let's get rid of the normal force. Mu times mv squared over r equals mg. Well, this is probably no surprise by this point, but the masses cancel out, which is a good thing. Basically, that tells us that this ride is going to work for everybody. It doesn't matter whether you're old or young, tall or short, skinny or not skinny or otherwise, whatever your body size and shape is, this ride is going to work for you. Now the question is, what's mu? So mu is, if we move things around, we got g on this side, multiply both sides by r, so we got rg, divide both sides by v squared, we got over v squared. Mu is rg over v squared, so it's going to be 2 times 10 over v, 6.28 squared. Mu is whatever that is, 20 divided by 6.28 squared, 0.507. There we go. Doesn't actually have to be that sticky to keep you in the circle. Fun ride.